Okay, great. Hi, my name is Zhou Zhao. If it's hard for you to pronounce it, you can just call me Joe. And good afternoon. And I'm a fourth-year senior at Department of Chemical and Biomolecular Engineering, working for Professor Mabodin's research group. So today, my topic is glycol-inspired bandages. So first, I want to discuss how this is inspired by glycol. So as you can see, there are beetles, flies, spiders, and gecko. They can all climb on the wall. And how they can stick to the wall is there are those pillars or foot hair, whatever you want to call it. And those small things is in micro scale or nano scale. And it creates an intermolecular force between the feet and also the wall. And basically, it split one contact into several contacts. So the adhesion is increased by a factor of n to the 0.05 power. N is how many pillars there. So if you have one big pump and it's put on the wall, and now you consider you have so many foot hairs there, so that's increased by a tremendous amount. And the application for the bandage could be if you have a minor wound, or if you want to use a patch to monitor system, or you want to deliver drugs. And this is non-toxic. So it doesn't leave any chemicals on your skin. And it's repeatable adhesion, which means you can peel it off and put it back on and peel it off again. And of course, it's very easy to apply, and you can just rinse with water. Ideal condition is you can rinse with water and it's reusable again, and it's biocompatible. But after talking all these good things, we have a problem here. That's why I need to do research on. So if you can see this one, this is the sample we made, and that's the SEM picture. The diameter is about 5 micrometers, and the length is about 25 micrometers. And after we tested on glass substrate, we have a problems here. So as you can see, this is the perfect one, the ideal ideal situation. And now, after testing on glass substrate, those pillars collapse. So this is a problem. So the material we use in this case is PDMS. It's a polymer, if you don't know it. And so we use PDMS to fabricate those. We're going to go over the fabrication process in the next slide. And we use this one to fabricate those pillars, but they collapse. So we want to make it better. And by saying better, which we means is making the material itself stronger. So we want to increase the strength of the material, and there are two ways to do it. First, we can add in nanoparticles as reinforcement, and so make it stronger and avoid pillars collapse. Also, we can increase the amount of curing agent added, and we're going to go over curing agent in the next slide. If you have questions, just hold the thought. And so create a cross-linking. Also, we can make the material itself stronger. So here is the fabrication method. So in the beginning, so remember I was telling there are two methods. One is adding particles, one is increasing the curing agent. So if we want to add particles, so we add particles in the beginning. If we're just increasing the curing agent, we don't add particles at the start, but everything else is the same. So we mix PDMS, which we use is Sealguard 184, short value is 40. Short value 40 means the Young's modulus, which means the strength, it's the measurement of the strength of the material. So we mix with silicon in this case. And the size of the particle is 7 nanometers. And then we sonicate for 20 minutes and make sure those particles is evenly dispersed. And we mix with curing agent. So now is we can play around in this step. So it depends on how much curing agent we add in this step. So that can change the strength of the material. And we sonicate for another 20 minutes. So make sure both the particles and the curing agent is well dispersed. And we want to make sure there are no gas trapped in the sample. So we go through the desgasification process for 20 minutes. And after all this step, so we pour the PDM sample onto a silicon template with all these holes. And then we cure at a temperature of 60 degrees C for 10 hours in the oven. And after that process, we peel off the sample from the silicon template, and we have those PDMS Geico-inspired samples. So this is a thin film on the bottom, and this is about 0.005 inches. And then we have all the pillars right here, which is about 10 micrometers wide and 20 micrometers length. So it's a square, 10 by 10 square, and then it's 20 micron length. So here's the SEM pictures of the sample we have. So there are two types of samples. First one is pillars without any particles. So we just play with the current agent. So this is the perfect pillars, the SEM picture of the pillars. And also we have the one with samples. As you can see, there are some particles right here, also in the pillars. So this is the SEM image of PDMS mixing with particles. So now there are two things we need to test. One is we want to know how strong is the material itself, and also we want to know how what's the frictional force is, like how strong is the adhesion force. So we use this setup to test the frictional force. So we have a counter substrate. Usually in this case we use glass slide. So we have a counter substrate right here, and we have this, and then we have the sample right here, which we just made before. So we have the counter substrate, we have the pillar, and then we'll apply a load on the top. And then we'll have a pulley right here, and here is the weight which we use to measure the friction force. So normally what we do is there's a cup here, and we keep pouring water into the cup. So when the sample detached from the counter substrate, and that's when we record the amount of water in the cup, which is also the frictional force. And also we use this durometer to test the stiffness of the sample. So we make a bulk PDM sample, not this one, because this one is too thin. We make a bulk one, which is around 3 centimeters thickness. And then we use the durometer to test the stiffness. And after we did experiment, this is the first one is we play with the current agent. So by changing the amount of current agent, we can vary the strength of the material itself. So the first one is 10 to 0.5 mass ratio, and we keep increasing the current agent, the mass of current agent. So we go from 10 to 0.05 to all the way to 10 to 1.25. So as you can see, the Young's modulus, which is the stiffness, the strength of the material, goes up. And also we can increase the strength of the material by adding particles. And what we have done is adding black iron oxide, which the size is about 1 micron, and also silica particles, with the size is 7 nanometers. And both, we can see the strength is increased. Not a lot, but you can clearly see the trend. So this is black iron oxide, and this is the silica particles. And the next one is we test the frictional force. So we have 3 situations. We play with the current agent, the black iron oxide, and the silica. So the first one is when we have all the first one is the red one is the current agent. The x-axis is Young's modulus, it's the strength, which is this one. So the strength increase as we're adding more current agent. And the y-axis is the frictional force. So we see that as we're adding more current agent, the Young's modulus increased from left to right, but the frictional force actually dropped. So that's how we get, so we can increase the strength of the material, but we reduce the frictional force. And then we have the second scenario, we're adding black iron oxide particles, so which is the green one. So we have here, we can see as we're adding more particles, the frictional force dropped first and then increased again, which I will explain next slide why it happens. And the third scenario is when we're adding silica. So this is the one without adding silica, and there are 3 here. It's 2, 4, and 6% mass percent. So the frictional force doesn't change that much. And even we increase the Young's modulus, but we still keep a pretty high frictional force, which is the best situation. So we did more research investigation on why when we're adding the black iron oxide, it drops first and then increases again. So we took the SEM picture for 5%, 5 weight percent of black iron oxide, 15 weight percent, and 35 weight percent. So for 5%, as you can see, all the particles disperse evenly. So we know the pillar is well dispersed, which kind of makes sense because the pillar was pretty soft before. Now we're adding particles, basically make it harder, so kind of reduce the frictional force. And as we're adding 15 weight percent, as we're adding more black iron oxide particles, we make the material itself stronger, which kind of reduce the frictional force. But when we're adding a lot of particles, which the frictional force go back up. So we see here, it's much concentrated in this part compared to this part where it has pillars, which means there's a concentration gradient. So here it's very concentrated, and here it's less concentrated. So in the middle part, the sample middle part is very hard, and this part on the edge part is very soft. So we create a situation that is very soft on the edge, but very strong in the middle. So which yields the result that it drops here and then you go back up because it's very soft on the edge. And as a conclusion, so there are 3 ways we can change the material strength and play with the frictional force. First is adding, we can vary the amount of curing agent we use. And then we can also adding the iron oxide particles, which is in micro scale, and we can also adding silica particles, which is in nano scale, and which yields different, 2 different size particles yields different frictional result. And we don't know for sure if it's the particle size or if it's particle itself. So our assumption so far is that the size. And also we can add more curing agent by create a cross-linking structure and make the PDMS stronger. And our future work is we're going to change the aspect ratio, which is the length of the pillar over the diameter of the pillar. And we need to test the frictional force. Also, we want to test the frictional force on a softer substrate. So currently, we're using a glass substrate. And now we want to move on to a softer substrate, which is more similar to your skin. So skin is not as hard as glass. And the third thing is we want adding nano carbon tubes, which is the tube. Before it was particles, and now we have a tube, which is very good for shear stress. So this is all the things we can do in the future. And I would want to thank Rose Hills Fellowship Foundation, the Bolian Research Group, and the National Science Foundation for providing me these great opportunities. Thank you so much.
Great presentation by Joe. We have time for maybe one question, if we, yeah.
Fascinating, by the way, but my question is, how is it that decreasing the surface area actually increases the adhesion? Wouldn't a standard surface area?
Oh, like in the beginning of the presentation?
Right.
Right. So before, even though suppose my hand is on the wall, but if you have a microscope or SEM, you can see it. There are actually spaces between.
Right.
So if we have those nanoscale and microscale pillars that kind of fill up the space, create an intermolecular force, even though it's not strong, but we have 1,000 tons of those pillars, make it really strong. That's why gecko can climb on the wall.
Great stuff. I think I've got to keep things to basically 15 minutes. I think we'll thank Joe again for a really great talk, and then we'll bring our next presenter up.